Recursive, it's nonsensical.
Are you calling my life's work nonsense?
Hi everyone, in this CSE 373 review video, we're going to be talking about how to go from code to a recurrence. And you can think about this as just an extension of the code modeling techniques we already learned, except now we can analyze recursive code. First, let's recap the basic structure of a recurrence. So a recurrence is a piecewise function that has a base case and a recursive case. And for each of our cases, we can see the amount of work done in each case and under what conditions our case will be called. So here at the top, we have our base case, which is called when our n value is less than 5, and we do 5 calculations in this case. Our recursive case down here, we can see calls itself 5 times, so calls our function 5 times, and each time our n, our input size, is being divided by 5. So we get that shrinking input size we see with recursive code and recursive functions that eventually trigger our base case. We also have this extra bit of non-recursive work here, which is executed every time that our function is called. So now let's go over some examples. First, we have a basic example. So feel free to pause here and take a little bit of time to try and solve this yourself, but I'm going to be going into it in like 5 seconds. Okay, so let's start. So first we want to identify our base case. So if we see here, the very first if statement, it says if n is 0, return 0. We're not making any other recurrent calls, so we can see that this is our base case, and it follows a similar format to other base cases that we've seen. So let's identify that as our base case, and since there's really only one calculation, we can just fill that in for our recurrence. So we can put in here one calculation if n is equal to 0. Next, let's identify our recursive case and our recursive work. So down here we see that our return statement calls our function twice. So we can put that in our recurrence, and we notice that each time our n, our input size, is divided by 2. So let's put that into our recursive function, and we get 2t n over 2. And now if we want to add our non-recursive work, it's these print statements. So we just add a +2 to our recursive case. Pretty simple, but now let's go over a trickier example. So let's start again by trying to identify our base case. This time it's not at the start, but if we see in the middle, we can see this if statement when n is less than 10, execute some code. So that's probably going to be our base case. So let's see what our base case actually does. So it looks like in the base case, there's a for loop that goes through n times and prints something out. So that's going to be n calculations in our base case. So we add that to our recurrence n calculations if n is less than 10. And now let's look for our recurrent case. So at the bottom here, we see all this recursive work being done. Our function is being called multiple times. One thing that you should be aware of is that if we are returning some number times our function or adding some numbers to our function, that's not actually calling that function more times. So we see here it says 5 times helper n minus 7. So that's actually not going to call helper 5 times, but just once. But we see in our return statement, our helper function is called 3 times. So we can pop that up into our recurrence function where we get 3t, and we know that our input size is decreasing by 7 every time, so we do 3t n minus 7 in our recurrence work. And now for the non-recursive work, we have this loop up here at the top that starts at our n value and goes to 0, dividing by 2 every time, so that's going to be log n work. So now let's go over this 8 queens problem, which is actually adapted from a CSE 143 lecture. So this function takes a board B, and the board is kind of, you could just think of as a list, and then a number column for that board. So an index and a list, basically. So we can already see right off the bat we have our base case, and I think there's a mistake on this slide. It's not supposed to be if n is less than 10, but if our column equals our board size plus 1. But we only do one calculation, so just in your mind, replace if n is less than 10 to if column is board size plus 1. And then for our recursive work, we can see that in this for loop, our function is called. You can see explore down there. And this loop has a potential to go through n times. So this loop could execute the code within n times, which means it could actually execute our function n times. So we're going to have n times t to the n, n times t of n, and each time our n is decreasing by 1 because we're getting closer and closer to the end of the board. But this actually, if you do the summation and do the tree method, the runtime for this is pretty nuts. It's going to be like O of n to the n, just because if you're calling your recurrence function n times, things get really crazy. And then the non-recursive work, we just add n because there's these other functions that are called in the loop, so n times, and each of them is constant. So now that we have our recurrence function, we can try to get our big theta by either using the master theorem if it's applicable. The master theorem has a certain format that our recurrence function has to be in, and if it's not, we can use our tree method to try and get our big theta.